Hello everyone. So today is the second day of Riemann sums, and today we're going to be talking about using Riemann sums with tabular data. These are very common questions on the AP exam. In fact, almost every single AP exam has one of these in the open-ended questions. So we definitely want to make sure that we are taking good notes and that we are understanding this topic. All right, so let's get started. Okay, so let's take a look at this first example. It says a school carnival sold raffle tickets as a fundraiser between noon, t equals 0, and 8 p.m., t equals 8. The number of raffle tickets sold t hours after noon is modeled by a differential function r from 0 to 8. R double prime is less than 0 for all t. Values of r of t and hundreds of tickets at various times t are shown in the table below. Okay, it's asking us to use a trapezoidal sum with 4 subintervals. So trapezoidal sum, hugely important, and 4 subintervals given by the table to approximate the integral from 0 to 8 of r of t dt. Does this approximation overestimate or underestimate the actual value? Give a reason for your answer. Okay, so we're going to start with just doing the first part of this question. Then we'll worry about the over or under approximation. All right, so trapezoidal sum with 4 subintervals. Okay, so if I look at my table, I'm obviously not given a graph, okay? First of all, you would think that your subintervals would be every 2 apart. If you're going from 0 to 8, divide that evenly, you get every 2. But that's not what we're given. If you look at this table, if you look at our x values, our t values here, okay, which we want to think of as our x's, all right, along the x-axis, we would say that they are not at all evenly spaced. We have 0, 2, 5, 6, and then 8. So, because of that, this is important to understand that our trapezoids do not have to be equally sized. It doesn't say 4 equal subintervals, it just says 4. So when we do this, we literally are going to kind of bracket off, and we're just going to make 4 brackets. So what you want to understand is that you do have to go, one bracket has to go from one table entry directly to the next. So that's our first one. Here would be our second one. Here would be our third one. And let me grab a different color. Here would be our fourth one. Okay? So those are our 4 different trapezoids. Okay, if the hours represent x, then we know that the number of tickets here represent y. So we're looking to find the area of these 4 trapezoids that would be created if I were to sketch these points and connect them. And we know, of course, that the area of a trapezoid formula is 1/2 the height, which the height is defined as the distance between your 2 parallel bases, times the bases, base 1 plus base 2. Okay, what I want you to understand is if you think about what we did last time, our height was considered the x distance. So this, your height is your x distance. And your base 1 and base 2 are your y values. How high up on the y-axis are you going? All right, so just keep that in mind as we think about our table. All right, so if I'm talking about the area altogether of what we have here, oops. All right, I would go ahead and say area is equal to, I'm going to pull that 1/2 out front. I can't pull out my height because, as I said, you can tell that from 0 to 2 would be a height of 2, whereas from 2 to 5 would be a height of 3. And so we do not have a consistent common denominator there, so we're going to have to put that in for each of them. All right, so 1/2 and then times. Now we're just going to kind of build each trapezoid independently. All right, so I would say the height of my first trapezoid was the distance between the x's, so 2, times base 1 and base 2 are the y heights for each of those, the number of tickets sold at 0 hours and at 2 hours. So that would be 0 plus 5. Okay, that's my first trapezoid. That's my blue trapezoid. Plus, moving on to the next one. Again, what is the height of my trapezoid? Well, it's the difference between the x's, so that would be 3. And then times my bases are the y values, which are going to be 5 plus 9. Okay, plus, moving on to my next trapezoid, the distance between the bases, or the distance between my x values is 1, and then my bases are 9 and 10. Plus, okay, we're moving on to our last one, and we would say that again, the distance between my x's is 2, so that's the height of my trapezoid. And my y values, my bases, are 10 and 11. Okay, so we're just going to go ahead and do some calculating to get our final answer here. So I would say 1/2. This would be 10 plus 14 times 3 is 42 plus 19 plus 21 times 2 is 42. All right, so we're going to add those together and take half of it and get our final answer. Okay, so I did some calculations and I found that I have a sum of 56.5, or I could say 113 halves. So either one of those would be my approximate area under the curve, okay? All right, now the next question asks us here, is this an over or an under estimate? All right, for the actual value. Well, let's talk about, if you remember last time, when you're talking about a trapezoidal sum, what matters is not if it's increasing or decreasing, but the concavity. So look back to the original problem. What about this problem tells us about the concavity? Hopefully your eyes are zooming into this right here. You are told that the second derivative is negative. If the second derivative is negative, we know that that means it's concave down. Okay, so looking at the y values, you can tell that they are increasing and we have a concave down. So remember I told you, if they're asking you this question, I want you to sketch a picture of what you're looking at. So I'm going to just sketch myself a picture of an increasing concave down function. So I would have something that looks like this. Okay, and then just remind myself, if I'm going between intervals of there and there, okay, I'm going to go ahead and make myself a trapezoid picture, and I can tell right there that that is definitely an underestimate. And the way that I would justify my answer or give a reason for my answer is I would say that r double prime of t is less than 0. And that is my justification for why it's an underestimate. All right, let's move on to the next one. Okay, so part B of this question says use a right Riemann sum. So a right Riemann sum with, again, 4 subintervals given by the table to approximate 1/8 the integral from 0 to 8 of r of t dt. Using correct units, explain the meaning of that in terms of the number of raffle tickets. Okay, so hopefully you're seeing that fraction in front. So what does it mean if we have that fraction in front, and especially if our interval is from 0 to 8? Well, hopefully you're thinking, oh wait, when we multiply by 1 over b minus a, that is the average value. Okay, so that's going to be our meaning, and we'll get to that in a minute. But first of all, let's actually do the computation, and then we'll express the meaning and the correct units for the raffle tickets. Okay, so right Riemann sum means we're doing rectangles, and we're working from the right, again with 4 subintervals. Okay, so let's take our table and break it down into 4 rectangles. And I think it might be helpful to start from the right and move to the left because we're talking about a right Riemann sum. So our first rectangle would be this one right here. Okay, and then we have this one right here. And then going this way, and then one more, we would have this one here. Okay, so as we're working through, we want to make sure that we're talking about the correct rectangle and that we are choosing the height from the right-hand side. Okay, so we know, of course, that the area of a rectangle is base times height. So my base, once again, comes from the x's and the height comes from the y's. And here's your x's, here's your y's. Okay, so I would say if I start with my blue rectangle over on the right. Now, you don't have to do this, but sometimes it just makes it helpful. Okay, the difference in the x's is going to give me my base, so that would be 2, and then I get my height from the right-hand side, which is going to be the 11. So 2 times 11 plus. Now I move on to my next rectangle. The difference in these bases is 1. Okay, and I would say that my right-hand side would be the 10 plus. Now I move on to the next one, and I would say that my difference in bases, okay, my difference in x's is 3 for my base, and my height is the right-hand side, so 9. Plus, last one, okay, again, the difference in x's this time is 2, and my right-hand side is 5. There will be one value here that doesn't get moved, that doesn't get used. The leftmost y value does not get used because we are talking about a right Riemann sum. Okay, so as I go ahead and compute this, I have 22 and 10 and 27 and 10. So let's see here, 22 and 27, that would be 49, 59, 69. Okay, but we need to be careful because if we look at what we were actually computing, we were computing 1/8 of that sum. So this is the sum here, and we need 1/8 of that. So all the way through 1/8. And so at the end here, I need 1/8 of 69, oops, which of course is 69/8. All right, that is my answer for this approximate 1/8 of the integral from 0 to 8 of r of t dt. Now it wants us to explain the meaning of that. Okay, so we already kind of talked about the fact that this 1/8 in front here is telling us that this is talking about average value. So now we just need kind of a concluding sentence that wraps up what that is. Okay, so we would say the integral, 1/8 of the integral from 0 to 8 of r of t dt is the average number of raffle tickets sold in hundreds of tickets from t equals 0 to t equals 8. Okay, so that concluding sentence, and we use the correct unit of measure in hundreds of tickets. We're talking about raffle tickets, and we're talking about the time that average is being measured. So that's how we conclude that answer, and we're all set with that. Okay, if we look at number 2, it says during the time interval 0 to 12 hours, water is pumped into a swimming pool at the rate P of t cubic feet per hour. The table below shows the values of P of t, a strictly monotonic differentiable function for selected values of t. Using correct units, explain the meaning of the integral from 0 to t, P of t dt, and 1/12, the integral from 0 to 12, P of t dt, in terms of the water in the swimming pool. Okay, so as we look at this, we have to write a couple sentences explaining what these each mean. And hopefully as you're looking at these, you notice the big fat difference is this 1/12. And of course the 1/12 should shout out at you, average. Okay, so what I'd like you to actually do is pause the video, either think, and if you're bold enough, write down a couple sentences that you think are the correct answers for what these mean. And if not, just at least get a good thought in your head, and then you can compare them to my sentences and get my sentences down in your notebook, and we'll talk about them. Okay, so you can see my two sentences that I have, and we're just going to kind of talk through them. The integral from 0 to 12, P of t dt, indicates the change in the amount of water in the swimming pool in cubic feet from t equals 0 to t equals 12, and we could say hours. Okay, so there's some really important features in this sentence. We want to make sure that we're using the word change or net change in the amount of the water. So what this integral is doing is going from a rate, that's what's given, okay, water cubic feet per hour, and the integral, okay, takes away the per hour and just measures how much water has changed in the pool in cubic feet from t equals 0 to t equals 12 hours. Okay, so that's super important. All right, the second sentence is for the average one. And so if I read this, it says indicates the average rate at which the water is pumped into the swimming pool in cubic feet per hour from t equals 0 to t equals 12 hours. Okay, when we are finding an average, we're finding an average of the rate. And therefore, the units do not change. That's hugely important that you understand, because a lot of times they're going to ask you for you to indicate the units of measure. So if you are finding an average, you don't change your units of measure. You're finding the average of the rate. The rate is measured in cubic feet per hour, so our average would be in cubic feet per hour. Okay, part B says use a midpoint Riemann sum with 3 subintervals of equal length. So we're talking about 3 subintervals. We're talking about a midpoint sum to approximate the 0 to 12 integral of p of t dt. Show the computations that lead to your answer. Okay, so we need to break this into 3 subintervals. If I look at my t, okay, what the time is being counted by, you can tell it's actually being counted by equal intervals of every 2 hours. And so I go from 0 to 12, counting every 2 hours, so it's easily, I can break this up into 3 groups of 4. So in other words, I have one group here, and then another group from 4 to 8, and then from 8 to 12. Okay, and each of those groupings have a middle value, and that's going to be super important because of course we know that the area of a triangle here is again base times height. But our base and our height for midpoint, okay, our base still comes from the distance between our x values. So again, base is the distance in our x values. But our height again is our y height. And we are taking the middle y height for a midpoint Riemann sum. Okay, so we're going to go ahead and say that we would approximate this area. Okay, so we're going to break this into the 3 rectangles. So the first one I have here was from 0 to 4. So I would definitely say the width of my rectangle, the base there, would be 4. And the height, well, I would get my height from my middle y value, which is going to be this y value right here, the 12. Okay, then I'm going to go ahead and add and go to the next rectangle. What I notice is that my next rectangle, my base goes from 4 to 8, and so that would be a length of 4 again. And my height will again take the middle y value, and that's right here, would be 25. Plus, okay, last one, again I have a base that has a length of 4, from 8 to 12 is 4, and my middle y value would be 50. So you can only do a midpoint Riemann sum from a table if they count evenly and if you have the equal exact middle between each of your left and right ends. So in other words, my left end of this first rectangle here would be 0, my right end would be 4, and the middle is exactly halfway between it, and that's why I can use the midpoint Riemann sum. Alright, so if we go ahead and compute this, we'd get 48 plus 100 plus 200, so that would be 348. It does not say that we need units of measure, and so 348 is our answer. We can leave it like that. Okay, if they had asked us for a unit of measure, of course we should know that it is cubic feet, and we know that because we integrated p of t, which was a rate of cubic feet per hour, so when we integrate that, we get just cubic feet. Okay, last question we're going to tackle today says use a left Riemann sum with 6 subintervals of equal length to approximate 1/12 the integral from 0 to 12 p of t dt. Hopefully your brain is telling you that's the average. Show the computations that lead to your answer. Does this approximation over approximate or under approximate the actual value? Justify your answer. Okay, so we're talking about this time left Riemann sum, 6 subintervals. Okay, so we're going to go ahead and again, left Riemann sum would be our rectangles, and so area is, again, base times height. And so we need 6 subintervals, and we go from 0 to 12, and we do, as we noticed earlier, these are equally spaced. So when I break up into 6 subintervals, it's simply going to be from every 2. So 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, and 10 to 12. So that makes our 6 different rectangles. And this time we are going from the left-hand side. Okay, so we're going to go ahead and start off by putting our 1/12 out in front this time so we don't forget it. Each of our bases here are a constant distance of 2 apart. So I actually could go ahead and pull out that common denominator of 2 if I wanted to. If it's easier for you to kind of think of each rectangle individually, do it that way. If you want to pull that common denominator out because they all have the same base, feel free to do that as well. All right, now I just need, if I pulled out my common denominator of 2, I just need the heights of each of the 6 rectangles. And remember, I'm going from the left, so I want the left-hand value of each of these, which is going to be my first value. So if I'm looking at my first rectangle, okay, then my left-hand side would be the 0. So I would go ahead and say 0 plus, now go on to the next rectangle, that would be 12 plus, and you're just basically adding down, but you're leaving off that last one. So that would be 20 for the third rectangle, and then 25, and then 30, and then 50. And if you count the number of heights we have in here, we have 1, 2, 3, 4, 5, 6, which indicates the 6 left-hand sides of our rectangles. So we have the right number of rectangle heights, and so we're all set. And they all had a base of 2, and that's why I was able to pull that out. Okay, so doing some computations here, if I multiplied the 2 and the 1/12, I would get 1/6 of. All right, so let's add these all up. So I'm going to start at the right-hand side here and add these up. So 80 for these two, plus 25 would be 105, plus 20 would be 125, plus 12 would be 137. So that would be the sum of everything in there, all my heights. And so I end up with 137 over 6 as my average value. And remember, we said average value keeps the units of measure, so that is in cubic feet per hour. So that's my answer. Okay, so now to the question of, does it over approximate or under approximate? Well, again, when we're talking about rectangles, the last time we addressed this, it was for a trapezoid. This time it's for a rectangle. Remember, when we're talking about rectangles, it doesn't matter about concave up or concave down. And in fact, you couldn't even tell with this. If you analyze this table, there's times when it looks like it's concave up and concave down. It's not consistent. And so we just know we have an increasing function, and that's all we need to know to analyze this. So if I took a look at an increasing function, and it doesn't matter, it can be either way, okay? It can go up and down, however. If I wanted to do a left Riemann sum between my intervals here of, we'll go from 0 to 12, just like they said, so from 0 to say 12, okay, well, I would draw in a left-hand rectangle. So starting on the left-hand side, I'd come up, and go across and drop down. And you can see that that rectangle clearly underestimates the area of the curve. So we would say an underestimate. And why would we say that? Justify your answer. Because this is an increasing function. So because P of t is increasing. And that would be our justification. Okay, so this concludes our lesson on Riemann sums, and hopefully you have a good handle on this. I know that a lot of, like I said, the first video was review from last year, but this, I believe, is all new. So we're going to do some good practice on it next time in class. Hope you have a great couple of days, and we'll see you soon. Thanks so much.